Hello, in this video we're going to be talking a little bit about the simple forces of flight. And we're going to do an example problem, kind of introduce some concepts that comes with these forces of flight. So we have four basic forces here. We have drag, thrust, lift, and weight. So all these four forces act on a plane when it's flying through the air, and we can do a lot of calculations given the relationship between all of these forces. So in basic aerodynamics, you'll come across a lot of problems where it says in steady flight. Now this means that the thrust equals the drag and the lift equals the weight. So it's flying straight as an arrow. The drag equals the thrust, so it's not accelerating in the front to back direction, and it's not gaining or dropping any altitude. The lift equals the weight. Okay, so we can do let's now do a basic calculation. So we want to calculate, given in steady flight, we want to calculate power required. So we want to calculate the power required to keep this plane in steady flight. So we have a couple of things we need to know. So the coefficient of lift for this plane is 0.15. The coefficient of drag is 0.031. The weight equals 5,500 pounds. And the plane form area is 225 feet squared. And the last thing we need to know is the altitude that this plane is flying at, and we'll say it's flying at sea level. Alright, so steady flight, thrust equals the drag, which helps us find the power. So the equation for power is thrust times the velocity, free stream velocity, or the velocity that this plane is traveling at. And there's no like wind coming at it or anything weird. So power equals thrust times velocity. And because we know that the thrust equals the drag, so we can say the power equals the drag times the velocity. All right. So we need to calculate the drag and the velocity. So to find velocity, we can use the relationship that weight equals the lift, so which then also equals dynamic pressure, Q infinity, times the plane floor area times the coefficient of lift. Dynamic pressure equals 1/2 rho infinity squared times plane floor area times coefficient of lift. So this is our dynamic pressure. So then solving for V, we have, so V infinity equals the square root of 2 times the weight divided by rho infinity times S times the coefficient of lift. And we know this plane is flying at sea level, so at sea. Density of the air is 0.00237 slugs per feet cubed. So we're using imperial units for this question. So plugging our numbers, velocity equals the square root of 2 times 5,500 divided by 0.002377 times S, which is 225, times coefficient of lift, which is 0.15, and we get our velocity to equal 370.3 feet per second. Alright, so now we want to calculate drag. Okay, so drag equals Q infinity times S times coefficient of drag. So Q infinity, so that equals 1/2 rho infinity V infinity squared times S times CD, so that equals 1/2. Density is the same, 0.002377 times our velocity squared, which would be 370.3 squared times plane from area, 225 feet squared, times the coefficient of drag, which is 0.031. Put all those numbers, we get drag equals 1,136.7 pounds. Drag. Alright, so now we have everything we need. We have velocity and we have drag. So now we can calculate power, which equals dV infinity. So that equals 1,136.7 pounds times our velocity, which is 370.3 feet per second. Solving for that equals 420,925.8 foot-pounds per second. So we want to find the power in horsepower, something we can understand a little bit better. So 1 horsepower equals 550 foot-pounds per second. Therefore, power equals 420,925.8 foot-pounds per second divided by 550 foot-pounds per second per horsepower. Then, solving for that, we have the power 765.3 horsepower. So a pretty healthy number for our horsepower. So that is the power required to keep that plane in steady flight. Quick recap here: 4 forces of flight in steady flight. Thrust equals drag, lift equals weight, which allows us to do a lot of calculations. Thank you.